Okay, so thank you, and also thank you for inviting me. Today I will talk about terahertz spin control, particularly about the new mechanism of terahertz-driven spin nonlinearity, but I will also present an interesting physics associated with the linear interaction between the terahertz fields and spins. So let me start by telling you that the work was done with the great support of Professor Alexei Kimmel and Professor Terahertz from Radboud University in Nijmegen. So a PhD student, Kirill Grushunin, helped me with the data analysis for one of the projects I will be talking today. So also other colleagues from Radboud contributed. So the majority of data I will show today come from the collaboration with the group of Professor Rupert Huber in University of Regensburg. So two PhD students, Sebastian Ball and Stefan Schlauder in Regensburg, helped me a lot with the measurements. So Professor Anatoly Zvezdin provided important theoretical support, and also other colleagues also contributed to the results. So since people are still coming, let me start with the outline. So first, I will discuss why we actually need to use terahertz fields to control magnetism. So then I show you a few examples of interesting physics associated with the interaction of the between terahertz magnetic field with the spins, and then move on to the terahertz nonlinear spin control. So first of all, let me remind you that magnetism is one of the strongest quantum effects manifesting itself on the macroscopic level, and magnetic properties of materials arise from electron spins, so the innate angular momenta of particles. And the quantum mechanics dictates that in many materials, the ordered state of spins when they are parallel or antiparallel is energetically more favorable with respect to the disordered state. And the reason for this is so-called exchange interaction, which is nothing else as the part of the electrostatic Coulomb interaction, which depends on the electron spins. Importantly, the typical energy scale of this exchange interaction, which also defines the intrinsic energy scale of magnetic system, is millectron volt. And the effective fields of this exchange energy, which holds spins aligned, can reach 1000 Tesla. So if one estimates the frequency of precession of a spin in such a high field, he would gain a femtosecond regime of precession. So therefore, it is actually very natural to expect that the magnetic system can respond to a very short laser pulse rather fast. And we already seen plenty of demonstration of the magnetization dynamics driven by ultra-short laser pulses. However, while being very fast, there is a certain drawback with the control with the ultra-short laser pulse. The photon energy exceeds the energy scale of magnetization dynamics by a few orders of magnitude, meaning that the largest part of the laser energy is idle with respect to the spin control. It would be much more energy efficient to find a way to control magnetic system simultaneously ultra fast, but also on its own energy scale. And the millectron volt energy corresponds to terahertz frequencies or picoseconds in the time domain. So therefore, terahertz magnetic field has been identified as the most direct interface to a spin. Indeed, it can simply exert a torque due to the Zeeman effect. So in this way, it was indeed demonstrated that a very short pulse of the terahertz magnetic field, which can reach 0.1 Tesla, can drive coherent oscillations in the archetypical antiferromagnet nickel oxide. However, here, only linear response was observed, which also implied rather small spin deflection, while the practical applications such as spin switching would call for the distinctly nonlinear regime. But before I will start to discuss the Terahertz-driven nonlinearities, let me also point out a few interesting effects associated with the interaction between the terahertz magnetic fields and the spins. So the first topic will be the Magnon-polaritonics. So at terahertz frequencies, so the spin precession or spin motion is the magnetic dipole active mode. So that's why it can absorb or emit terahertz magnetic field. But as you might know, the emission power of a dipole increases with its frequency squared, meaning that at the terahertz frequencies, the electromagnetic component of the spin wave is much more pronounced than in the conventional Magnonics at gigahertz frequencies. And that means that the spin waves on magnons at terahertz frequencies actually turn to be Magnon-polaritons, which can be illustrated in this graph. So if we have a dispersion line of light crossing the frequency of a magnon at terahertz frequency, then two hybrid branches will be formed corresponding to the lower and upper Magnon-polaritons. And the question I would like to answer today, whether we can see manifestation of these Magnon-polaritons in experiments. So the first system we looked at is thulium orthoferrite, which is counted antiferromagnet. I will talk about this material a lot today, but for now, the only important information you need to know is that it supports a terahertz magnon around 0.8 terahertz. So we performed first the terahertz time domain spectroscopy on this material. So the sketch of the experiment is shown on the slide. So we have an amplified laser, 800 nanometer wavelengths, femtosecond duration of the pulses, and the largest part of the laser beam illuminates electro-optical crystal, zinc telluride in our case, and due to the process of optical rectification, the crystal emits terahertz waves, which we can focus onto our sample, which sits inside the cryostat. So then the waves propagate through the crystal and are focused onto the second electro-optical crystal, which is simultaneously gated by the optical probe pulse, which is initially linearly polarized. So the electric field of the terahertz waves induces an optical axis in the crystal due to the Pockels effect, so as the gating pulse acquires ellipticity proportional to the terahertz electric field. And by changing the delay between the generation pulse and the probe pulse, we can record the time trace of our terahertz electric field. So that's what we see in the time domain. The waveforms transmitted through our samples. In the spectral domain, you can see a dip around 0.8 terahertz, which corresponds to the absorption of terahertz radiation by the antiferromagnetic resonance in this material. But if we have a closer look at the data in the time domain, you see that instead of the expected simple exponential free induction decay, we clearly see some sort of beating signals, which is unexpected. Of course, one may argue that this comes simply from some imperfection in our setup, and not from the sample itself. So we decided to check it further and perform a slightly different measurement, which is terahertz emission spectroscopy. So instead of generating terahertz waves outside from our sample, we now can illuminate the sample directly. Already from many talks from yesterday, you know that the ultrashort laser pulse can excite spin waves itself. And then, as this magnetic dipole active mode, it will emit terahertz waves, which we again are able to detect. So here are indicative emission signals. And again, you can see that instead of monochromatic signals, we see clear beatings or splitting of the resonance in the frequency domain. So it seems that beating is observed for both transmission and emission signals, meaning that it's something coming from the sample itself. So to reveal the physical origin of this, let us simply solve Maxwell equation for the given incident field, which is simply our terahertz pulse in the transmission geometry. So we also take the tabulated value of the magnetic permeability function for the antiferromagnetic resonance of thulium orthoferic, which is reported in the literature. And without any fitting parameters, we can nicely reproduce the beating in the time domain or splitting of the mode frequency in the spectrum. So then we repeated analysis for the emission geometry. Here, the situation is a little bit more complicated because we have the laser pulse which excites the spin precession, and this obviously goes beyond the standard linear electrodynamics. So we assume that it acts as an effective magnetic field which follows the intensity of the laser pulse being Gaussian, and then again we can calculate the terahertz emission based on Maxwell equation. And again, we obtain the beating in the time domain or splitting of the resonance frequency in the frequency domain. And the only fitting parameter there is the amplitude of the light-induced effective field, which can be known a priori. We can also, in our calculation, vary the thickness of the sample, and as for both transmission and emission cases. And as you can see, the splitting of the mode becomes more and more pronounced as we increase the thickness of our sample. All these facts point to the fact that this beating arises from simple linear propagation of our magnons. And what so we can, with the known permeability, we can even calculate exact dispersion around the antiferromagnetic resonance frequency in this material. And what we see is essentially nothing else as the beating between the lower and upper Magnon-polariton branches. And here, in the region of anomalous dispersion, the waves cannot simply propagate. So the propagation effects are important, and the question is, can we employ this scenario for terahertz spin control? Yes, please.
First, permeability, the magnetic permeability that you put in, that must have also the Magnon response in it.
Could you specify your question?
Yes, what I mean is, in order to get that, you use the magnetic permeability.
Exactly.
Yeah, but it must have the property of the material in order to get this the response out.
Yes.
Yeah. So what is it that precisely you put in? That is what I'm trying to understand.
Yeah, the tabulated value for the
frequency dependent.
So it was measured before simply by the Fourier spectroscopy, which allows you to extract the exact shape, the both real and imaginary part of the permeability, which has a standard Lorentzian shape. So the amplitude is known, the width is known, and then you just simply put it into the Maxwell equations. So this is essentially empirically defined function from the previous literature. And it is material specific, of course. So yeah, so the next point is to see whether propagation effects are present in terahertz spin control. So here,
excuse me,
yes.
a short question. This mechanism you described, does it occur just when you excite a resonance with the magnon, or also if you excite it in a more resonant fashion? So do I need to have the magnetic field of light oscillating at the frequency of the magnon to have this Magnon-polaritons, or if I excite it in another way, like a random mechanism, so the frequency of light is totally different regime?
So the excitation mechanism doesn't matter, as you could already see. In both cases, once we excited it with the terahertz magnetic field in the transmission geometry, and we also excited it by this impulsive stimulated Raman scattering by this short laser pulse, in both cases, you observe beating. So essentially, what is important is indeed that your excitation must be broadband to excite both polariton branches. If it will be a narrow frequency, pure resonant excitation with the magnetic field, so like in the Fourier spectroscopy, for example, of course you will never see this beating because you will only excite a certain point in this dispersion line. So that's exactly, so this beating is indeed a consequence of the broadband excitation when you excite both polariton branches.
And temperature effects, so is it effect temperature dependent? If you hit sample, does it increase, does the signal increase or decrease? Because it should, if you have more magnets.
So the effect is more pronounced indeed at low temperature as the damping of the magnon becomes smaller. Another condition you need to satisfy is, of course, the high quality factor. Because if the beating time will be smaller than the decay time, you won't observe it as well.
When you have that, you had a frequency plot, yeah. But actually, then if you vary the frequency, and you have a broadband, then it actually means that at one frequency you have some shape. You understand me what I mean? That so you do not exactly vary the frequency, but you have in order to get the both branches, you have to have the broadband effect.
Yeah, but that's. If we come back here, so this is the excitation spectrum, for example, and of course it's much broader than the shape of the line, and the laser pulse is also, since it's ultra short, it's sort of very broadband excitation. So okay, so the next experiment we did, it's similar material, dysprosium orthoferrite, and we pumped it with a strong terahertz pulse. And then we measured the spin dynamics in the sample directly by detecting the Faraday rotation of the near-infrared femtosecond pulse delayed with respect to the terahertz magnetic field, which is also shown here. And again, we have the broadband spectrum between 100 gigahertz to 2 terahertz. Importantly, we cut the sample perpendicularly to its optical axis to suppress the effects associated with the crystallographic birefringence, which can essentially diminish our Faraday rotation. And important information about this material for now is that it supports 2 orthogonal antiferromagnetic resonance modes, and there is a temperature around 150 Kelvin when the frequencies of these modes become equal to each other. So let's see what happens around this temperature. So here I show you the signals at different temperatures. They indeed consist of two contributions at two frequencies. So one corresponds to the quasi-ferromagnetic mode, which involves a rotation of magnetization with the constant length, while another quasi-antiferromagnetic mode involves the change of the length of the magnetization without changing direction. And as you can see, these modes are indeed orthogonal to each other. And we also confirm that they cross. The frequencies cross over. But if you look carefully in the data in the time domain, you see that around the crossover temperature, the amplitude of oscillation significantly increases. And it seems it's not a simple superposition of the amplitudes taken away from the crossover temperature. This becomes even more apparent if you look in the frequency domain. So here you see that the spectral weight of the sum of the modes at the crossover temperature is not simple sum of the spectral weights of these modes away from the crossover temperature. I can even integrate it and show the integrated amplitude as a function of temperature, and indeed it peaks around the crossover point. So what can it be? This behavior resembles a behavior expected for the so-called internal resonance phenomenon. So imagine we have two harmonic oscillators, which in our case are these two modes of antiferromagnetic resonance, and we introduce some coupling between them. So I took the simplest one, but the same effect will be observed for other coupling terms. So then we can find a response in the frequency domain, and additionally to the standard Lorentzian terms, there will be additional contribution, which peaks when the frequencies of the modes become equal to each other. For some indicative parameters, I can also find the integrated response as a function of detuning between these frequencies. And again, you see it peaks as the frequencies of these partial oscillators become equal to each other. So it seems that there must be some coupling between the magnons in our experiment. However, there is an obvious trouble because these magnons were derived from the equation of motion of spins in an antiferromagnet, and by definition, they are orthogonal to each other. So the first candidate for coupling is nonlinearity. So maybe Terahertz-field drives spins so strong that the deflections become large and the magnons orthogonal to each other in the linear regime start to talk to each other. So we did experiments for rather small and larger Terahertz driving field strengths. So here you see the normalized signals with respect to the Terahertz field. And you essentially see that the signals are practically identical to each other, meaning that there is no nonlinearity in the system.
What is the spin-probe field for this material? So how close are you a larger field to the spin probe?
Well, we are very well away. It's 10th of Tesla. The anisotropy in the orthophrite is very strong. So that's not the nonlinear coupling. And I will argue that, again, this is nothing else as the propagation of the electromagnetic component of these spin waves, which is responsible for the coupling. So from the previous experiment, we already know that this is it's not just magnons, they are polaritons. And they must propagate as any electromagnetic wave. And they propagate inside material with a certain dielectric properties. Particularly, orthophrites are highly birefringent crystals at Terahertz frequencies with rather different components of the dielectric tensor. In fact, the difference in velocity between the ordinary and extraordinary waves at terahertz frequencies in the ultraviolet is larger than that at optical frequencies in crystallographic quartz. Moreover, the difference between these tensor components are much larger than any variation of magnetic permeability, meaning that propagation of the Magnon-polaritons are governed practically exclusively by dielectric properties. So then I would like to remind you that our crystal was cut perpendicularly to the optical axis at visible range, which set the direction of propagation. However, the optical axis at terahertz frequencies is 15 degrees away from optical axis for optical waves, meaning a strong birefringent effects are possible in our measurements. So before, when these normal modes were derived, one assumed that, say, this ferromagnetic precessional light mode polarized in the xy plane were interacting with the field polarized in the same plane, while another orthogonal mode was polarized along the z direction, and also it interacted with the field in the same direction, and by no means these orthogonal modes can be coupled. However, this xyz for our propagation direction is not anymore the right basis of the system. Instead, it is set by the polarization of the ordinary and extraordinary electromagnetic waves set by these tensor components. And if one combines the equation of the spin motion together with the Maxwell equation in that case, we'll immediately see that these quasi-ferromagnetic and quasi-antiferromagnetic modes are not the normal modes of the system anymore. So you can look at it like this. So imagine initially you have your dipole polarized along the z direction, then it emits the electromagnetic field, which propagates inside the birefringent material, so getting another field components which act on the neighboring magnetization, which can also be polarized in x and y direction. So what we see the internal resonance mediated by the lattice or dielectric properties of two antiferromagnetic magnets.
Excuse me. So what is the relation between the propagation of the terahertz magnons in respect to the anisotropy of the antiferromagnet? Is this a uniaxial antiferromagnet or is it biaxial?
So the optical anisotropy is in principle not connected to the magnetic anisotropy. So to formally answer your question, so it's biaxial magnetic anisotropy and it's also biaxial optical anisotropy. However, the optical anisotropy is set by the dielectric tensor and not by the magnetic properties. So essentially the optical axes do not coincide with any magnetic axis.
The coupling to magnons that are set up by the magnetic anisotropy. That's what I'm asking.
So as I explained, the coupling between the magnetic fields of light and the magnons are set by the optical anisotropy. Because otherwise, it's, so the coupling itself is simple Zeeman coupling. So the anisotropy defines the exact, so it defines the frequency of the magnon. And it defines, also in the case of the quasi-ferromagnetic mode, the ellipticity of precession. But it doesn't define the coupling with the light field. So this is what I wanted to tell you about the linear interaction. Let's now turn to the terahertz nonlinear spin control. But why do we need to do it? So let's assume we want to realize terahertz-driven magnetic recording and we want to switch magnetization to the opposite state with the help of the short pulse of the terahertz magnetic field. To do that, we need to drive the system over the potential barrier, which separates these opposite states of the magnetic order parameter. And in that case, calculations show that the fields required are well above 10 Tesla, which in the terahertz regime is well beyond the capabilities of the current sources available. The alternative approach would be to use not the magnetic but electric field of the terahertz wave, which can bring the system into the strongly non-equilibrium state in which the potential barrier separating these two states with opposite magnetic orientations can be diminished, making the system much more susceptible to the spin switching. And the idea here would be to employ the electric field to pump the low energy electric dipole active excitations coupled to magnetic order. So here, of course, you may say that this is very indirect mechanism. But at the same time, you should bear in mind that electric dipole oscillator strength is typically 6 orders of magnitude larger than that of magnetic dipole. And the candidate for these dipoles are the orbital states which set magnetic anisotropy in many transition metal oxides. These orbital states are split by the crystal fields, and the splitting lies in the milli-electron volt regime, so it can be directly addressed by the Terahertz-pump. So the idea is to repopulate this orbital state to change magnetic anisotropy and then drive spins into motion. So the question is, of course, how strong this effect can be. So to answer this question, we performed the experiment on thulium orthoferrite. So now I will tell you a little bit more about this material. So it has 2 magnetic sublattices coupled antiferromagnetically, while the orientation along which the spins are aligned is set by the orbital state of thulium ions. So at the very low temperature, only the lowest sublevel of thulium ground state is occupied, and it favors the alignment of the spins along the z crystallographic axis. As the temperature goes higher, the higher orbital states becomes occupied simply due to the Boltzmann distribution, and at some point the orientation of spins in the orthogonal x direction becomes more energetically favorable. So as the system between 80 and 90 Kelvin exhibits the so-called spin orientation when the magnetic structure continuously rotates in the xz plane. So I will illustrate it in the cartoon in a moment. So we start from the low temperature, then we populate the higher levels, and magnetization and the magnetic sublattices rotate. So this is, of course, equilibrium thermal process. The question is, can we do it now in a non-equilibrium way? So we can sit in vicinity of this phase transition, and instead of simply heating the sample, we can come with the terahertz wave and resonantly repopulate the higher orbital states, changing the electronic orbital of thulium, which exert a torque on spins. So this I illustrate again. The terahertz pulse comes, repopulates, which means a sudden change of magnetic anisotropy in this material. So this is the scheme of our experiment. Again, we pump our sample with the terahertz pulse, and then we trace magnetization dynamics by measuring the Faraday rotation of the femtosecond probe. So here is the indicative shape of our terahertz pulse, and the spectrum covers both modes of antiferromagnetic resonance in this material, as well as several transitions within the thulium ground state. So here are indicative signals at different temperatures. So again, they correspond to the superposition of the two modes, quasi-ferromagnetic and quasi-antiferromagnetic. We can also map the frequencies versus temperature. And as you can see, one of the modes, namely quasi-ferromagnetic, precessional-like mode, softens at the temperatures of the phase transitions, meaning that this mode is expected to be highly sensitive to the change of the magnetic anisotropy in this material. So what we can do now, we can sit in the middle of this spin instability temperature interval and start to increase the driving field strength. So here you see the signal in the time domain at the rather low driving field strength, which corresponds to the excitation of only high-frequency quasi-antiferromagnetic mode. However, as we increase the driving field, the signal changes qualitatively, meaning a nonlinear regime of excitation. So here the spectra are normalized with respect to the Terahertz driving field, and as you see, while the normalized amplitude of the high-frequency mode stays roughly the same, the low-frequency soft mode appears for the high driving fields. We can even plot the amplitudes of these both modes as a function of the driving field, and as you can see, quasi-ferromagnetic mode demonstrates a clear nonlinear behavior.
How you discern this pumping effect from temperature effect? Because if you increase the power of this pulse, then you increase the heating itself.
So that's will be discussed anyway. So the short answer, as you see, the mode frequency is strongly temperature dependent, and we tried hard to see any shift of frequency here, and we observed no within our resolution at least. So we estimated that the heating of our sample was less than 0.1 Kelvin. So it can be clearly ruled out. Right, so the question is now, what is the origin of this nonlinearity? So first of all, you might well know that the equation of the spin dynamics are nonlinear themselves. Maybe again it's just this nonlinearity of the spin motion which leads to this effect. So we solved the Lagrangian equation of motion of spins in response to our Terahertz magnetic field, and for the fields available in our experiment, we observed that there is no deviation from the linear behavior expected, meaning that the isolated interaction between the spins and the Terahertz magnetic field cannot account for our experimental observations. At the same time, one may notice that the symmetry of the crystal allows for the light spin energy term quadratic with respect to the Terahertz electric field. So here theta is an angle between the antiferromagnetic vector and the x crystallographic axis, meaning that this term has exactly the same symmetry as the magnetic anisotropy. And it can be seen that the Terahertz electric field changes suddenly magnetic anisotropy in our material. Moreover, we can plot the temperature dependence on this energy term, and we see that it's only non-zero in the narrow spin instability temperature interval between 80 and 90 Kelvin, exactly where we observe our nonlinear excitation of quasi-ferromagnetic mode. So it seems the simple phenomenology is supported by the experimental data, but the question is, how can we connect it to the microscopic population of thulium states which rule magnetic anisotropy in this material? So first of all, we confirmed that in our sample, we have several absorption bands in the terahertz range associated with the different transitions between the Thulum states. And what we can do now, instead of using a rather broadband excitation, which can excite several Thulum modes as well as both modes of iron system, we can now cut away of high frequencies in resonance with the Thulum and start to pump ferromagnetic mode selectively. And if our interpretation is correct, then we would observe an absence of nonlinear excitation. Okay, so here the light gray is our original driving spectrum. So after an application of the low-pass terahertz filter, we have only the low frequencies left. And indeed, in that case, we observe the excitation of quasi-ferromagnetic mode, but it scales linearly with the terahertz driving field, exactly as required for the Zeeman excitation by magnetic torque. In the complementary measurements, we actually cut away all frequencies in resonance with this mode. And despite there are no frequency components anymore which can directly drive this mode in our material, it is still excited with the higher amplitude, and it scales purely quadratically versus driving terahertz field. In that way, we indeed confirm that our terahertz pulse can modify the orbital state of Thulum ray Earth, thereby changing the magnetic potential function for the iron spins and drives them into motion. Moreover, our estimations show that for the highest field available in our experiment, this anisotropy-driven nonlinear torque was already 1 order of magnitude stronger than the torque exerted by the terahertz magnetic field in that case. So we also tested that this effect is present in other materials such as dysprosium or ferrite. Here, there is a little bit different phase transition around 50 Kelvin when the magnetic structure changes from the purely antiparallel to a countered state. And it is another quasi-antiferromagnetic mode, which is the soft mode in this case. And not surprisingly, we observe nonlinear excitation of this another soft mode around 50 Kelvin. So the effect seems to be rather general. So to sum up, I hope that I convinced you that there are interesting physics associated with the propagation of polaritonic effects at terahertz frequencies. And we can also find a new way for the terahertz nonlinear spin control based on the excitation of the orbital states which control magnetic anisotropy. However, we are still well away from the required terahertz-driven magnetization switching. So the dream would be to use a short terahertz pulse to inverse the polarity of a magnet as it does a laser pulse, but here with much lower photon energy. So what I demonstrated so far was nonlinearity of the spin response with respect to the driving terahertz field. But we didn't observe any nonlinearity in the spin dynamics itself, which is essentially a signature of the switching. For example, one may use some modeling for Thulum orthoferrite in this spin instability region. If we come with the terahertz pulse just above 10 Tesla, using the Zeeman torque, we can switch antiferromagnetic order parameter. However, if our anisotropy torque doesn't saturate, it can switch antiferromagnet even for much lower terahertz driving field of the order of 1 Tesla. And obviously, the response will be strongly anharmonic. So with our field of 0.3 Tesla, we actually were not that far away from this switching threshold. Unfortunately, we used the maximal field available by our terahertz source. But can we somehow enhance this available terahertz field? And one of the options is to use near-field enhancement in the plasmonic antenna. So we fabricated this gold bow tie antenna on top of our thulium orthoferrite. So here we have a gap which serves as an effective capacitor, increasing locally the terahertz electric field. And our calculations show that this enhancement can be even higher than 25 times. So what we can do, we can illuminate this antenna structure with our terahertz pulse, and then again measure Faraday dynamics inside this antenna gap. So since our calculations show that the near fields exceed 10 megavolts per centimeter in the center of the gap, this anisotropy torque can be already sufficient for 90 degrees spin switching. Okay, so very recently we did this experiment, and I show you the first results. So we start for the low driving field strength, and again, as you can see, we observe the excitation of this quasi-ferromagnetic mode. However, as we increase the field up to 0.75 megavolts per centimeter, in the frequency domain, you clearly see a splitting of the Magnon resonance, which corresponds in the time domain to the phase sleep. So then we can increase our driving field further, and this phase sleep or splitting of the mode becomes even more pronounced. So these are very first results, and the details will come soon. With this, I would like to thank you for your attention.